So welcome all to week 8 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR IT Bombay. So topics that we're going to cover today includes convex set, then we'll go to convex function, and towards the end we'll look at some basics of optimization. Okay. So let's begin with defining what's a convex set. So the simple definition for convex set is, so if you have a set and you have a line joining 2 points within this set, then your line should remain within the set. So to formally say, line joining 2 points in the set is contained in the set. For example, if you look at these two examples, in the first one, no matter where you draw, you take any 2 points, if you draw the line, it remains within that set, right? Whereas in this case, if you take a point here and if you take a point here, the line goes outside the set. Okay, so you can take more examples. For example, in a square, if you take any 2 arbitrary points, the line will remain within the set. Okay, and other example can be, for example, if you take a star or something like that, which is shaded, right? Then again, if you take 2 points, you will go outside the set. Okay, so the definition for convex set is pretty simple. Line joining any 2 points remain within that set. Okay, now we can formally define this thing, or we can mathematically define this thing. So let's say we have a set S, and let x1 and x2 be any 2 arbitrary points from this set S. Okay, then what is the equation of line joining these 2 points? So equation of this line, then the equation of this line would be given by alpha times x1 plus 1 minus alpha times x2, right? This is the equation. So this belongs to your set S for all alpha in range 0 to 1. Okay, then we call this set S. Then S is convex if this thing happens. So if this condition is satisfied for every pair of x1 and x2, then we call our set S to be convex set. Okay, so just a slight motivation. So if you look at any 2 points, let's say this point is x1 and this point is some x2, in this equation, if you replace your alpha to be 0, then you will obtain x2, right? And if you replace your alpha to be alpha to be 1, because your alpha is in range 0 to 1, right? So if you replace your alpha to be 1, you will get the point x2. And what would happen, let's say if you have alpha is equal to half, then you will get x1 plus x2 divided by half, somewhere in the between. So x1 plus x2 divided by half, right? And similarly, if you will keep on changing your alpha, you will get this complete line. That's why this is the equation of line joining x1 and x2. Okay. And in a convex set, this complete line should remain within that set. Then only it's called a convex set. Okay. Let's look at some of the examples. So let's say this A1 set is given to be x comma y belonging to R square. So it's a 2-dimensional shape. So let's draw a 2D figure. We'll draw our shape here. And it says x plus y is less than equal to 4. So let's say x, this is my 4 comma 0, this is 0 comma 4. Then my line x plus y is equal to 4 is this line, right? And it says x plus y is less than equal to 4. So the region would be this region, right? Anything on left of this line. So this is sort of my half plane. If you look at it carefully, this is the equation of a half plane. And if you can clearly see that if I take any 2 points on this side, if I draw a line, it will always remain on this side of the line. Okay. So this A1 set is a convex set. Okay. Similarly, if you want to draw A2, you can draw A2. Give me a second. So let's say I want to draw my A2 set. Okay. So the equation says that my y square is greater than equal to 6x, right? So let's first try to draw y square is equal to 6x, then we can take care of the inequality. Okay. So what is my y square is equal to 6x? So if you have something like this y is equal to x square, then you have a parabola of something of this shape, right? And if you have, let's say, x is equal to some y square, then you have a parabola of this shape, right? So it would be a parabola centered at 0, something like this, right? So this is equation of y square is equal to 6x, and we want y square to be greater than equal to 6x. Okay, so yeah. So you can clearly see if we keep on increasing the value of y at a particular value of x, then this equation gets satisfied. So the region that this is referring to is the outer portion of this parabola, not the inside of the parabola. Okay. So it is referring to this portion of the parabola. Okay. Okay. So now if you carefully see, if you draw, take 2 points, let's say one here, one over here, and you draw a line joining these 2 points, then this line certainly does not lie completely within the set A2, right? So the set A2 is actually not a convex set. Okay. So I think now if we look at the options, first option is correct that A1 is convex, but A2 is not. Okay. One more example that we can do over here is, let's say we define a set A3 to be y square is less than equal to 6x. Then my set would have become this shaded region, right? So inside of this parabola, then this A3 set would have been a convex set. This A3 is a convex set. Okay. So this was about convex set. Now let's move on to something called convex functions. Okay. So one important thing is like why is convex set studied in sense of optimization? So the reason is when you find minima over convex sets and convex function, or you try to optimize a function over convex set and convex function, then there are many great techniques. So in what sense they are great? So you are guaranteed convergence, they are computationally inexpensive. Okay, so there are these kind of techniques that people have proposed for this kind of setups. That's why if you look at optimization lectures anywhere, they will start with convex set and convex function. So many a place they have a specialized course on convex optimization. Okay, so that is a different thing. Okay, so now let's go to something called convex function. So intuitively what a convex function is, let's say this is your function. So this thing that I'm highlighting is curve of your function. Okay, this is your function. Okay, now what a convex function is, if you take any 2 points, let's say you take this point x and y, right? You took this point x and y, and you joined f of x and f of y. So you drew a line from f of x and f of y. Your function in this portion will always remain below this point. Okay. So this is the definition for your convex function, that if you take any 2 points and you join points f of x and f of y by a line, then the value of that function always remains below that line. Okay. So as I mentioned while defining a convex set, if you have 2 points x1 and x2, the equation of line joining x1 and x2 is given by some lambda times x1 plus 1 minus lambda times x2, where your lambda belongs to 0, 1. Okay. So this is the formal definition, that the value of function at any point in between this. So this is your x and y. So if you take line joining x and y and you look at the function value at any point on this line, that is always less than the value of this line that you have drawn between f of x and f of y. So this is the line between f of x and f of y, right? So this is the definition of your convex function. And intuitively what I said is, if you take any 2 points and you draw a line between f of x and f of y, your function values always remains below this line. Okay. So this many a times is also referred as zeroth order characterization of convex function. So there are 3 equivalent definitions for a convex function. One is just via value of f of x and f of y. One is via gradients and one is via Hessian. So this one is called zeroth order characterization. And one via Hessian is called first order, one via gradient is called first order, one via Hessian is called second order characterization. Okay. So let's look at some examples. So this is the first example that we have. We are given with the function f of x is equal to mod of x. Okay. And we are asked, is this a convex or not? Okay. What is meant by strictly convex is, so I had a less than equal to over here. Okay. If I replace this less than equal to by strict inequality, then we can have a definition for strictly convex. Okay. So let's look at the function that is given to us, mod of x. Okay. So we all know how mod of x looks like. Okay. So mod of x looks like this, right? Now, if you take any 2 point on your function and you draw a line joining these 2 points, you can clearly see that in this region, the value of your function, so in this region, the value of a function always remains below this line. Okay, that's why this function is a convex function. Okay. One important property of convex function is that it has only one local minima. I'll come to the definition of local minima and those kind of things. But if you have a convex function, then you have many beautiful optimization techniques, okay, that are easy to do. So your gradient descent will always converge to global minima and those kind of things. Yeah, so I'll come to the definition of local minima, but for the time being, I'm mentioning it. Okay, so this one we want to sort of prove via definition. So it's a very easy function. This is your function that f of x is equal to x square, right? We want to show that this is a convex function. If you look at the characterization that we have given, you can clearly see that the function remains below this line, but we want to sort of theoretically show this thing. Okay. And I want to show you that showing this theoretically is not very easy. It might require some tricks even for simple functions like x square. Okay. And that's why we have more characterization of this that helps us easily check whether an arbitrary function is convex or not. Okay. So what did we had in our definition? That f of lambda times x1 plus 1 minus lambda times x2 is always less than equal to lambda times f of x1 plus 1 minus lambda times f of x2. And my lambda belongs to 0, comma 1. This is what we have to show. Okay. Let's, okay, from where should we start? Should we start from left side or right side? Let's try to start from left side only. Okay. I think, yeah, we can start from left side only. So what is this f of lambda x1 plus 1 minus lambda x2? This is lambda x1 plus 1 minus lambda x2 square, right? So if you just expand this, this is lambda square x1 square plus 1 minus lambda square x2 square plus 2 times lambda into 1 minus lambda x1 x2. Okay, and you want to show this that this is less than equal to what? So we'll also write what we want to show. We want to show that this is less than equal to lambda times of x1 square plus 1 minus lambda times of x2 square. Okay, you can see that it's not very straightforward. From going here to here, it's not pretty straightforward. Okay, so we use a trick over here. Okay, so the trick that we use is, so what is this x1 minus x2 whole square? This is given by x1 square plus x2 square minus 2x1 x2, right? And no matter what is the value of x1 and x2, because this is a square, this term is always greater than equal to 0. Okay, so this would mean that my x1 square plus x2 square minus 2x1 x2 is always greater than equal to 0. Or what would it mean is that my 2x1 x2 is always less than equal to x1 square plus x2 square. Okay, so we will use this particular identity and put it over here. Okay, so now we are replacing it via this 2 times x1 and x2, this 2 multiplied by x1 and x2. We'll replace this by x1 plus x2 square, x1 square plus x2 square. So what we will have? We will have a greater than equal to sign over here, right? So this is lambda 1 x1 square plus 1 minus lambda square x2 square plus 2 goes away. Now there is no more 2. There is just lambda times 1 minus lambda uh, x1 square plus x2 square, right? Okay. So we now just have to keep on evaluating this. We take x1 square common, then we have lambda square and plus lambda into 1 minus lambda is lambda minus lambda square plus 1 minus, sorry, then again we take x2 square as common, then we have 1 minus lambda square, right? Then we have plus lambda into 1 minus lambda, right? So if you evaluate this thing, this becomes x1 square. These things get cancelled out, so you have only lambda left. So we can just rewrite it cleanly as lambda times x1 square plus you can take 1 minus lambda common over here. Then whatever is left inside is 1 minus lambda plus lambda times x2 square. This lambda and lambda get cancelled, so you eventually get lambda x1 square plus 1 minus lambda x2 square. So because we had this less than equal to in between, so we can say that this condition is satisfied for x square and hence x square is convex. Okay. So if you ask anyone about a convex function or like whoever has studied about convex function, even now if I ask you give me an example of a convex function, then the easiest example that comes to your mind is x square, right? Something that is bowl shaped so that you draw a line, your function values remains below that line. But even for such a simple function, we had to use this trick right? The proving was not straightforward by the definition that we mentioned, okay? So the definition that we mentioned, the zeroth order characterization, is the definition for convex function, but using that it is not very straightforward to prove or check whether some function is convex or not, okay? So we will have more characterization of this that we'll see shortly, okay? Okay, I think I should do the characterizations first, okay? So I'll do the characterizations first, then I'll come to this local minima and global minima and all those kind of business, okay? So the first characterization is, I'll draw and then sort of explain. Okay. So I'll take the example of x square only. Okay. So if you draw a tangent at any point, okay, for the functions for which your tangent is defined, for example, if you took mod of x, then this property you can't use because tangent is not defined at this particular point 0. Okay. So for the points where tangent is defined, right? If you draw a tangent, your function will always lie above the tangent. Okay, no matter where you draw your tangent, you will clearly see that if you draw a tangent at any point, your function will always lie above that tangent. This is also an equivalent definition, or you can say it as a property or an equivalent definition for convex function. And this is how you mathematically write it. Okay. So this function, this property says tangent always below the curve. You can look at an example, like for example, if you have a function like this, okay, and you drew a tangent at this point, okay, then it will cut down your function and your function is not always lying above this thing. Okay, so this is not convex function. Okay, so this was one characterization. This was by gradient, and the most useful one, I would say, or the most easiest to check whether a function is convex or not, is the second order characterization, that is via Hessian. So last time we covered what Hessian is. So if you have calculated the Hessian matrix of a function, this denotes the Hessian matrix of function, and if this is positive semi-definite, then also your function is always uh, convex. Okay, this is another characterization. So checking positive semi-definite will come to this, but just remember that if you have your Hessian and you check whether that is positive semi-definite, then you are done. You have confirmed that it is a uh, convex function. Okay. Okay. So now we come to something called as local minima and global minima. Okay. So first of all, what is a local minima? So if you have a function, let's say you have a, so let's say you have a function, something like this. Okay. So I think I can draw something better. Uh, okay, let's draw a sine curve as an example. Okay. Okay. So let's say this is the function that you have. Okay. And now what is the local minima? So a point x is called local minima. So let's say this is your point x. You will call this point a local minima if in its neighborhood. So if you look at the small neighborhood of it, this point, this is the minimum point. So this function attains minimum value at this point in a small neighborhood of this point. Okay, so if, okay, I'll use the black only. If there exists a delta, so this symbol is for there exists a delta, so that for all y belonging to x minus delta to x plus delta. So this denotes a small neighborhood of this point. So you are taking, this is, let's say, your point x, so you are looking at some x minus delta and some x plus delta. Okay, if you take any point in this region, then f of y is greater than equal to f of x. So in this region, your function attains minimum value at this point. Okay, then your x is called as a local minimum. Okay, and this also is a local minima. Again, you will have other local minimas, and this orange points that I'm marking, this is a local maxima, this is a local maxima, this is a local maxima. Okay, so similar to local minima, you can also define local maxima, that in a small neighborhood it is the maximum point. Okay, now what is global minima? Okay, so global minima is the minimum value of a function on complete domain. So these are, so I can just modify this picture. Okay, I think I didn't want it to erase the complete photograph picture. So let's say this function looked something like this rather than what it looks. Okay, so this is also a point of local minima. This is also a point of local minima, but the function attains a lower value at this particular point, right? So this we will call as the global minima. We will obviously check over all the local minimas, and wherever it attains the minimum value would be your global minima. Okay. So now why are we talking about local minima and global minima? So again, let's get back to machine learning. In machine learning, you have some loss function or the error function, that more generally it is called loss function. Okay. That you want to minimize, right? So you want minimum error. Okay. And the method that I think right now we have discussed is gradient descent, right? So the most commonly used method is called gradient descent. We'll discuss this in more detail, I think, in the next lecture. So if you have a non-convex function, okay, a function which is not convex, then you might get stuck in local minima. Okay, and if you have a, let's say, a convex function, if you find a local minima, that is guaranteed to be a global minima. So very loosely speaking, if you have a convex function, it will have only one curve like this. So it can't have multiple curves like this. Okay. So it will have only one curve. So that kind of functions are generally convex. Otherwise, let's say over here you could have drew a tangent and it would go above that line, above the function. Okay. So you will only have one such thing. For example, here also if you drew a tangent, let's say over here, it will not always remain below the function, right? So yeah. So this was the motivation behind this local minima and global minima. Okay. Okay. One more small thing. There is also something called concave function. So concave function is something whose negative is convex. So it would look something like this. So these kind of things are called concave function. Okay. So when you are maximizing, you look for concave functions. When you are minimizing, you look for convex functions. Okay. Okay. So this is what I wanted to say here. Then we'll go to some more things. Okay. Okay. So any doubt in whatever we discussed till now? convex function, characterization of convex function. We'll obviously solve some examples now, but before that, any doubt in this? I'll do this. If you have any doubt, you can type it in the chat box or you can unmute and ask. Any doubt related to convex function, three characterizations that we have done, convex sets. Okay, so if there is no doubt, I'll proceed. I'll solve some questions based on this. Okay, so now I told you that this third property that we had, that is our second characterization, is the most easiest or the most useful one to check whether a function is convex or not. Okay, for that what we have to do is we have to just check that Hessian is positive semi-definite or not. Okay, so whether a function is positive semi-definite, right, positive or negative semi-definite, positive definite, right, or negative semi-definite. I think we did this during linear algebra course via these two approaches. I'll just repeat those approaches for someone of you who might have forgot. Okay. But the last approach, this principal minor approach, was not done in linear algebra portion. Okay, we will do this today over here. Okay. And I'll try to be very elaborate about this because this is the easiest among these three to check whether a matrix is positive semi-definite or not. Okay. Okay. So let's say your matrix is Q. You want to check whether your matrix Q is positive definite, positive semi-definite, negative definite, negative semi-definite, or if it is none of these, you call it indefinite. Okay. So what is the first property or the definition is, if X transpose QX is greater than equal to 0 for all X, for any arbitrary X. Okay. If this thing happens, then that matrix Q is positive semi-definite. One thing, you check this property definiteness of a matrix Q only for symmetric matrices. Okay, so you should remember this thing. So whatever we are talking about, we are just talking about symmetric matrices. Okay. So first thing that I said is that if your Q X transpose Qx is greater than equal to 0 for all X, then your Q is called positive semi-definite. Now checking it for arbitrary X is very, very difficult, right? So this is the least easiest way to check whether a matrix is positive semi-definite or not. Okay. So I'll just give you alternate definitions. If you have X transpose Qx strictly greater than 0 for all X, then it is called, then Q is positive definite. Okay. And you can have, now you might have got the pattern. If it is less than 0 for all X, then it is negative semi-definite. Okay. And if this thing is for all X, then Q is negative definite. And if it does not satisfy any of this, none of this, then it is called indefinite matrix. Okay. Like for checking the convexity, we are just interested in the first one, that it is positive semi-definite or not. But other definitions are also many times useful, so I'm mentioning it over here. Okay. Second property, the second way to check whether a matrix Q is semi-definite or not, positive semi-definite or not, is via eigenvalues. Okay. So you, let's say you find these are all eigenvalues of Q. So first task would be that you calculate all eigenvalues of Q. Okay. Then if lambda I is greater than equal to 0 for all I, that is all of your eigenvalues is greater than equal to 0, then Q is again positive semi-definite. Okay. Similarly, if all lambda i's are strictly greater than 0, then Q is positive definite. And now you have got the pattern. Q is negative semi-definite. Okay. And lambda I is strictly less than 0 for all i's, then Q is negative definite. Okay. Again, calculating eigenvalue is also not that pleasing task, I would say. Not that easy. Sometimes your characteristic polynomial that you get might not factorize further. Okay. So now we will go to the easiest method using principal minors. Okay. So first of all, you might know what a minor is. Let's say you have a matrix Q. Let's say something like 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If you, let's say, delete some row or you delete some column, okay, then whatever is left is called minor of that matrix. Okay. So this 5, 6, 8, 9 that I have left is a second order minor of my matrix Q. Okay. So you just remove some rows or columns, some row, some column, then whatever is left is called your minor of your matrix. Okay. Now, okay, this you might have used when you used to calculate inverse of a matrix, right? So what you used to do is, if you, let's say, looking at this position, then you used to black out this row and this column and then look at the determinant and then write it down. That you used to call as minor, right? So you can delete any row and any column and you will get a minor of Q. Okay. Now there is something that is called as principal minors. Okay. So what is principal minor? So let's say if you remove the kth row, then you must remove kth column. Okay. So you are not, for example, in this case, we remove the first row and we remove the second column. That is not allowed over there. In order to obtain principal minors, you must remove the same numbering. Okay. So you can remove, let's say, okay. So for example, you can remove first row and first column. Okay. Then you will get a principal minor. Okay. And how do you define order of that particular principal minor? So a k order principal minor, order k principal minor is obtained by deleting n minus k rows, right? So yeah, so this is how you obtain. For example, this one is not a second order because you removed one row. Okay, so you have deleted one row from here. So yeah, this is a second order. Yeah. No, sorry. Let me get this nomenclature correct. It is obtained by deleting n minus k rows. Yeah, I think this is correct. Is it? Yeah, this is correct. Okay. Okay. So you can just look at the size of minor that is left. That is same as your order. If you carefully look at this definition, what it is saying is that you delete n minus k rows, right? So how many rows are left in total? Let's say there are total n rows, right? And you delete n minus k of them. Then you have k rows and k columns left, right? So the size of the minor that you get is your order. Okay. So I have defined what is principal minors. So let's look at an example. Okay. So let's call this matrix, let's say Q, and this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So what is, so I'll use this triangle 1 to denote all the first order principal minors. So as per the definition, you have to remove 2 rows and 2 columns. Okay. So first option that you can have is you remove the first row, second row, and first column and second column. Okay. So this thing goes out, this thing goes out, this thing goes out, this thing goes out. What is left? 9. Another option is you can remove the first row, first column, then third row and third column, right? Then you have something as left as 5. Last option that you have left is you don't remove the first row, you remove the second and third row and second and third column. Okay. Then you have left 1 with you. So these are your three first order principal minors. That is 1, 9 and 5. They are eventually the diagonal entries. Okay. Okay. Now 1, 2, 3, 4, 5, 6. Okay. Now let's look at the second order principal minors. So in order to obtain second order principal minors, you have to remove 1 row and 1 column. So for example, if you remove first row and first column, okay, okay. So this is the principal minor that you get. Okay. 5, 6, 8, 9. Right. The second one that you will get is you remove the second row and second column. So you will get something like 1, 3, 7, 9. And similarly, you can define one more over here. And third order would be the complete matrix Q. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. This is how you define your minors. Okay. I'll use a slight abuse of notation. I'll tell you what I'll do. Okay. Now there is also something called as leading principal minor. This is slightly different from what is done in the course. So this is called leading principal minor. Okay. So what is leading principal minor? So as per the definition, if you look, the leading principal minor of a matrix A of order K is a minor of order K obtained by deleting the last n minus k rows and column. Okay. So this deletion of rows and columns that we were doing has to be done from last. Okay. So you will delete the last rows and last columns. For example, if you want to obtain the order 1th leading principal minor, so you have to remove 2 rows and 2 columns. So the rows that will be removed would be from last. So last row and last column, then second last row and second last column. So you will only get 1. So you could have many principal minors, but you will have only one leading principal minor. Okay. Similarly, for order 2, you will just remove the last one. So your order 2 would look something like 1, 2, 4, 5. Okay. So this is how you can obtain your leading principal minor. Okay. Now I have defined what minors are. The term that I am interested in is the determinant of these minors. Okay. So this this delta that I introduced, I said that I am using an abuse of notation. The quantity that I am interested in is the determinant of these values. Okay. So this 2 cross 2 matrix determinant. Okay. So that I'll denote by this triangle 1 or delta 1 or delta 3. Okay. And similarly for these things, I'll define, let's say, D1 to be the norm of size 1 leading minor. or the determinant D2 as determinant of size 2 leading minor and D3 as my determinant of size 3 leading minor. Okay. So I think now is clear about, you people are now clear about what do I mean by dk and lambda k. So these are the determinant of these minors that I have defined. Okay. Now, based on the values of your dk and delta k, okay, I'll use some different kind of d so that you don't confuse it with delta. Okay. You can infer whether a matrix is positive semi-definite, negative semi-definite, and those kind of things. Okay. And here is the characterization. Okay. What does first one says? So one thing is clear, you have lesser number of leading principal minors as compared to your total number of principal minors. Okay. So in order to check your positive definiteness and negative definiteness, you only need to look at the leading principal minors. Okay. So what does this say? If all your decays, that is the determinant of your leading principal minors, is greater than equal to 0, sorry, is greater than 0, strictly greater than 0, then your A matrix is positive definite. Okay. For negative definite, you have minus 1 to the power k dk greater than 0. So your first one should be negative, that is order 1 should be negative, order 2 should be positive, order 3 should be negative, and so on. Okay. If something like that is satisfied, then it is called negative definite. Okay. In order to check for positive semi-definite, you need to check for all principal minors. Okay. Now you don't have to just check for leading principal minors, but for all principal minors. That is your delta k. And similar definition holds for negative semi-definite. Again, the alternating one. Okay. Okay. Any doubt in this before I can solve examples based on this? Okay, probably I'll start with the example. Okay. Okay. So this is the matrix that is given to me. Okay. First of all, what I'll do is I'll calculate D1. Okay. So what is my leading principal minor? It would be 3, right? And its determinant is also 3, which is strictly greater than 0, right? In order to obtain D2, okay, I'll use a different color pen. This is D2, and D2 is determinant of this thing that I have sort of boxed in green, and that is 3001 determinant, that is 3, right? Which is again greater than 0. Okay. Now let's look at D3. D3. D3 is the determinant of complete matrix, right? And is given by 3, 0, 3, 0, 3, 1, minus 2, minus 2, 8. Okay. This you can evaluate as 3 multiplied by 8 plus, okay, so this is minus 4. Yeah, minus 4 plus 3 multiplied by, this is 0 minus 3. Okay. So this is 3 4s are 12 minus 9, which is again 3, which is greater than 0. Okay. So we have D1 greater than 0, D2 greater than 0, and D3 greater than 0. What does this give us? This gives us that the matrix that we had is positive definite. Okay. So one thing that you might be clear by now is positive definite implies positive semi-definite, right? If a matrix is positive definite, then it is obviously positive semi-definite because we had x transpose qx greater than 0 and greater than equal to 0 condition, right? So if you show that it is positive definite, then it is definitely positive semi-definite also. Okay. So when you will have to check this condition is, let's say your one of this d1, d2, d3 comes out to be 0. Then you might be interested in other principal minors and then evaluate it. Okay. Otherwise, you would be okay just by checking this first one. Okay. Okay. So now let's try to solve this one more example. We have to determine the definiteness of this symmetric matrix. Okay. So again, d1 norm of determinant of this 1 is greater than 0, right? What is d2 determinant of this 2 minus 16, that is minus 14 is less than 0. Okay. And the third one is, okay, third one would be, why don't I have some good colors? Is it visible on the shared screen? I hope so. This D3 we can have something. But if you look at the conditions that we had, either we wanted first one to be negative and second one to be positive. So we don't have any option where we have first one positive and second one negative. So this particular combination that we have, it does not fall under any of the categories that is written over there. So it is an indefinite matrix. Okay. Okay. So this is an example I think from previous year. This is related to positive definiteness. I request you guys to please attempt it, give 4 or 5 minutes to it, and then I can solve this for you. So it is given that this matrix is positive definite. Okay, positive definite it is given. Okay, and you have to find the value of k. It might not be a single value, it can be a set of values. Okay, so that this thing is positive definite. Okay, so you just need to find d1, d2, d3 and pose a condition that it is strictly greater than 0 and see what is the value of k that you can obtain. I request you to please attempt the question so that we can solve this. Somebody says 2 by 7. We'll wait for others also to solve. Okay. Somebody else also says 2 by 7. We can have 1 more minute and then I will try to solve this thing. We can wait for 1 more minute for others to solve and then we can solve this. So if you look at our D1, yeah, we define this positive semi-definiteness or definiteness only for symmetric matrices, right? You are correct. Okay. So our D1 is just 2, which is anyway greater than 0. Okay, somebody says A and D, we'll solve it now. Okay. So if we look at D2, this is the norm of this matrix. This is 2k. So if you want this to be greater than 0, the condition it gives us is that your k should be greater than 0. One condition is this that you have obtained. Okay. So we can highlight this, that I want my k to be strictly greater than 0. One thing is that we have obtained. Then if you look at D3, so you have to now calculate the determinant of this matrix. This is 2 times 4k minus 1, right? And then 1, and this is 0 minus k. I hope I'm doing it correctly. Okay. Okay. So this would give us, if we want this thing to be strictly greater than 0, this implies that 8k minus 2 minus k is greater than 0, or k is greater than 2 by 7. Okay, k is strictly greater than 2 by 7. Okay, so now this is another condition that we have obtained. So we want both these conditions to be satisfied, that my k is greater than 0 as well as k is greater than 2 by 7. So what is the common region among these two? The common region is k is greater than 2 by 7. Okay, so this fourth option is the correct answer. Okay. Fourth option is correct. So because we had both this condition and we want both this condition to be satisfied. So it is something like k is greater than 0 and k is greater than 2 by 7. So that's why we take sort of intersection of both these things. So if this is your number line, so if this is 0, this is 2 by 7. K greater than 0 means this region, and k greater than 0, 2 by 7 means this region. So we take a region which is satisfied by both of these. Okay, so we take k greater than 2 by 7. I hope Ravi Shankar it is clear. Okay. So this is the answer for this. Okay. Okay, yeah. So this is another question. What is the condition on alpha for which this function is convex? Okay. So again, what is the condition for convex? Condition for convex is that your Hessian matrix is positive semi-definite. Okay. And this is a function of just one variable. So Hessian is nothing but f double dash. Okay. Hessian is nothing but f double dash. So second derivative of this function. Okay. So you just need to check the second derivative that you get, that is a single value. It is positive semi-definite. So what is meant by that? That this value that you will get should be greater than 0, or greater than equal to 0. So I'll solve this because it does not involve a lot of things to do. So f dash x is so 2 alpha minus 1 x to the power 2 alpha minus 2 it would become, right? And then f double dash x is 2 alpha minus 1 multiplied by 2 alpha minus 2 x to the power 2 alpha minus 3, right? So we want this thing to be greater than equal to 0. Okay, so this value x, because it's from 0 to infinity, right, will always be positive. So we can just ignore this thing for the time being. Okay, and focus on rest of them. So we want this thing to be 0. So we will get the product to be 0. So we want this 2 alpha minus 1 into 2 alpha minus 2 to be greater than equal to 0. So it is possible under two situations. First is that my 2 alpha minus 1 is greater than equal to 0 and 2 alpha minus 2 is also greater than equal to 0, and the second condition is, or this is 2 alpha minus 1 is less than equal to 0 and 2 alpha minus 2 is less. So even if both of them are negative, their product would be positive, right? So from here we obtain something like alpha is greater than equal to half and alpha is greater than equal to 1. So something similar to what we did in the previous question. So let's say this is half, this is 1, then alpha greater than equal to half, and alpha greater than equal to 1. I hope these colors are differently visible. I should use a more contrastive theme probably. Yeah. Okay. So the solution is from here, from this branch we get alpha is greater than equal to 1, or let's see what we get from here. This is alpha is okay, so this is and over here. So alpha is less than equal to half, and alpha is less than equal to 1. Okay. So if you draw something similar, so this is half, this is 1. So this region is alpha is less than equal to 1, and we can have something like green representing alpha is less than equal to, yeah, this is what I didn't want it to do, that it overshadows that thing. Yeah, probably, yeah, this color works fine. Okay. And alpha is less than equal to half. So what is the common region? Common region is that my alpha is less than equal to half. So yeah, so this is alpha is less than equal to half, or alpha is greater than 1. So fourth option again is correct. Okay. Okay. So right now I just did a question with one variable. Now this is a question with two variables. That is the least that we should at least do. Okay. So this is a function. Okay. So we have to check whether its Hessian is positive semi-definite or not at 2 points we are given. So at both the points we have to check. Okay. So first thing would be to calculate the Hessian, then evaluate at these points, and then check at these points. Okay. So what I can do is I can solve for W, this Hessian at W, and then you can try for point V. Okay. So let's go step by step. I won't jump any step. Okay. So what is Hessian of f? You might remember this is fxx, fxy, fyx, and then fyy. So partial derivative with respect to x, then again with respect to x, with respect to x, then with respect to y, yx, yy. Okay. So in order to calculate this, what is f of x first? This is the equation that is given to us. So this is the function that we have. Okay. So partial derivative with respect to x is 3x square minus 12y, and we have no terms having x in the last component, so 0 from there. Then what is f of y? F of y similarly is, we don't have any y term in the first component, then minus 12x plus 24y square. Okay. Okay. So now we can have all these four components. F of x is given by 6x, right? F of xy is given by minus 12, right? And again, f of y is given by 48y, right? 12, 24, yeah, 40. And then f of yx is given by minus 12. Okay. So what is my Hessian matrix? Hessian matrix is given by 6x minus 12 minus 12, 48y. Okay. And we have to evaluate this at certain points. So we are given first point is, first is w is equal to 1 comma 2. Okay, so x is 1 and y is 2. So Hessian of f at w is given by 6 minus 12 and 48 into 2 is 96. Okay. Okay, this is just 2 cross 2 matrix. So what is D1? D1 is nothing but your this 6, right? What is D2? D2 is this 96 into 6 minus 144. So this is 6, 6, 36, 3. This is definitely positive, right? Whatever it is, this is positive. So you got both D1 and D2 to be strictly positive. So this matrix is positive definite. And also you can say it is positive semi-definite. Okay. So can you just look at the value of this Hessian at this second point and then check whether it is positive definite or positive semi-definite, whatever it is. At point 0, 1, what is the value that you obtain? This is 7:13 right now. I can give you 3-4 minutes. 7:17 you can try. Remember that at one point you might get 0, one of the leading principal minors. Then you will have to check for all principal minors in this case. Okay. So just remember that. I've also given you the formula for Hessian. You just need to calculate the Hessian at this point and then check for its positive semi-definiteness or definiteness, or whatever it is. Okay, somebody says A is the answer. Okay, that might be possible. We'll have to check. Somebody says C is the answer. Okay. I'll just also just go up and show you what is the condition to check negative semi-definite. So this is minus 1 to the power k, whatever it is. Okay. And similarly for dk and this delta k. I'll get back to the question. Take 1 or 2 more minutes. You can try solving this. Okay, I'll start doing. Okay, so we calculated the Hessian for general point x comma y. Now we have v given to us. So let's see. Do I have some more color that I can use? Probably purple here. Yeah. So yeah. So just a second. Yeah. This is given by sorry. So Hessian at point V is given by, so V now is 0 comma 1, right? And this is what we have calculated as our Hessian. So the matrix boils down to 0, minus 12, minus 12, and 48. Okay. So now if you look at our D1, D1 is 0 and D2 is minus 144, right? So for negative semi-definite or negative definite, we wanted that our D1 should be minus 1 to the power. Okay, so what we wanted is that minus 1 to the power 1 D1 should be greater than equal to 0. Or what does this mean is that minus of D1 should be greater than 0. This condition is definitely not satisfied because it is 0. We will see to it. And we wanted our second condition to be minus 1 to the power 2 D2 is greater than 0, or this would mean D2 to be greater than 0. This is also not satisfied. So there is no point now checking for principal minors, because D2 is also one of the principal minors. It is the leading principal minor, but it is also one of the principal minors. So this minus 1 to the power 2 lambda 2 greater than equal to 0 will not be satisfied, because for one of them we have already got this to be negative. Okay. So that's why the second term is indefinite. So yeah, so the C option is correct, that at point W it is positive definite, and at point this it is indefinite. Okay. So when do you call a function convex then? Like if it is at some point positive definite, at some point negative definite, then it is not a convex function. For all points, right? For all points, if it is positive semi-definite, then only you call function to be convex. Okay. Okay. Now that's it that we had for convex function and convex sets. We will do some other topics. Okay. So this Taylor series again is an important topic in mathematics or engineering mathematics that might be useful for you many times when you are probably deriving your gradient descent, right? Or in other context it can be proving something. There also it might be important. Okay. So what does Taylor series approximation give you? So you all might know this. Let's say you know function value at point x. Okay, you are comfortable at point x and you want to approximate the function value at some x plus h, where h is very small. Okay, so you want to approximate this value at some nearby point, and you have access to values at point x. Okay, then the Taylor series approximation gives f of x plus h. So value at f of x plus h is nothing but value of function at x plus f dash x divided by 1 factorial multiplied by h. Okay, then h square by 2 factorial multiplied by f double dash x, and so on. You can keep on going. It's an infinite series sum. Okay, that is equal to your x plus h. Okay, this is for one dimension that I mentioned. So your x is one variable. Oh, sorry, f is a function of only one variable x. Now, if you have a function of multiple variables, so this x that you are seeing over here, x is actually, let's say, x1, x2, xn. So f is a function of x1, x2, xn. Then all this notion of derivative get replaced by similar notation in multivariate calculus. So your f of x plus h then is given by f of x. Now, you can't just simply multiply by h, because if your x is something like x1, x2, xn, then your h would also be something like h1, h2, right? You are incrementing in every direction. Okay. So then you multiplying by h is similar to multiplying by its transpose, that is taking dot product with a gradient. Earlier you had f dash x, now you have gradient. Okay. Again, for the second term, you have Hessian. And similarly, higher order derivatives, which is again not very easy to like visualize. Okay. So generally you stop at 2 and then you assume rest of them to be error in your calculations many times. Okay. So this is your multivariate Taylor series expansion. Okay. Okay. Any doubt till this point? Then we will now uh, like cover some basics of optimization. In next session, we will have more detailed discussion on optimization. Today, we'll just touch upon some basics of optimization. If you have any doubt, you can ask, please. Okay. So I'll just try to answer that question. See, I hope my screen is visible. Yeah. So Alvin, like if you look at this theorem or the condition, the first condition, whenever you have to say whether it is positive definite or not or negative definite or not, then you just need to check on the leading principal minus. So this dk, I'll just go to that screen. I'll erase this whatever I have written. Okay. So in order to infer anything about positive definiteness or negative definiteness, we just need to check leading principal minus. Okay. So if you have this d1, d2 or whatever you are obtaining, this all to be greater than equal to 0 or less than equal to 0, then you should only be restricting yourself to leading principal minus. Okay. But if any of this d1 or d2 or dn comes out equal to 0, any of them comes out equal to 0, then you also need to check for the positive semi-definiteness. Okay. That maybe it is greater than equal to something. Then you have to check all the principal minors. Okay. I'll just reiterate. If all d1 dn are either greater than 0 or less than 0, then you need not check for all principal minors. Then you can just infer based on this whether it is positive definite, negative definite, or indefinite. If any of them turns out to be 0, then you should check for all principal minors. Am I clear? Okay, thanks. Okay, let's so this whatever we are talking about optimization is going to be very elementary, because next session we will dive more deep into optimization basics. Okay, so what is an optimization problem? Okay, so in mathematics, in optimization problem, you have to either minimize or maximize some function. This can be function of single variable, multiple variables. Okay. For example, if somebody is asked you what is minimum of x square. Okay. So what you will say that the minimum value is 0 and it is attained at x is equal to 0. Okay. This was a pretty simple example. So you were able to say straight away. Okay. So this is a very basic uh, optimization problem. Okay. This f of z, okay, is called your objective function. Okay. So your objective is to minimize or maximize this thing. So this minima or maximum of this is called your objective function. So if somebody asks you what is your objective function, In this example, it was minimize x square. So minimizing x square was your objective. So this is called as objective function. Okay. Now let's say in this question, I add a twist. I say, tell me the minimum of x square when your x is greater than equal to 4. Okay. So let's say x is equal to 4 is this point. Then in this region, I'm asking you, what is the minimum value of my x square? Okay. So if I impose some extra conditions, for example, x is greater than equal to 4 or x is less than equal to some alpha, okay, any condition I impose, these extra conditions are called constraints. So I want to minimize or maximize my objective function, but I also want some condition to be fulfilled. Okay, those conditions are called constraints. Okay, so I hope that was clear. Next thing that we look at is something called as feasible region. Okay, till now what I have done is, let's say I have some objective function and then I have some set of constraints that it is less than alpha, g to z is greater than equal to some beta or something like this. You have list of constraints and you have an objective function. Okay. So if you look at all constraints and look at the region satisfied by all constraints. Okay. So region satisfied by all constraints is called your feasible region. Okay. In short, it is the portion in which you should search for your minimum, this optimal value. So this is the value that is satisfied by all constraints. Okay. So if I give you some constraints, this is the region in which all your constraints are satisfied, and so you should look for its solution only within this region. Okay. This is your feasible region. Local minima we have already discussed. What is the local minima? That in a small neighborhood, it is the minimum point of that function. Okay. So if you look at, let's say x is local minima, if there exists some delta, so that if you look at x minus delta and x plus delta, any y belonging to this set, your f of x is always less than f of y. Okay. 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 As I said, this is just elementary things on optimization. So if you want to bifurcate the complete area of optimization into broad categories, you can come up with 2 to 3 categories. Okay, so one, you can categorize this on basis of linearity. Okay, if your objective function and all your constraints, okay, are all linear, okay, then you call that optimization problem as linear optimization. Okay, and there are methods like simplex method which are actually very good in this region. Okay, in this particular category. Okay, and if any of these, either your objective or any of your constraint is non-linear in nature, for example, I said in my constraint, I said over here that my x is greater than equal to 4. This is a linear constraint, but my objective function was non-linear. Or I could have optimization like this, and I could have said square root of x. Okay, I should change the color. Okay, again, very bad choice. I'll probably erase. If I said something like square root of x is greater than equal to 4, right? Then I had a non-linear constraint. Okay, so those kind of category comes under this, which is called as non-linear optimization problem. Okay, so this is one bifurcation. Another bifurcation that happens is on basis of convexity. Okay, so again, here also, if your objective function plus the feasible region are both convex. So we define convex set and convex function both, right? So if both of them are convex, then we call this as convex optimization problem. If one of them is not convex, then it comes into the category of non-convex optimization problem. Okay, I'm just mentioning it so that if you maybe give some interview sometime, somebody asks you what, because these are elementary things, and like you should just know the definitions. Okay. Okay. So there is few more things that people use generally. One is called, okay, uh, linear optimization is also sometimes called as, I'll use the same color, as linear programming problem. Okay. So linear optimization is also called as linear programming problem, or LPP in short. You might have heard the word LPP. Okay. So similar to LPP is something that is called as IPP. Okay. Or integer programming problem. IPP is integer programming problem. Okay. So what is an integer programming problem? So you have some objective. So mean f of z. You have some constraints similar to whatever we have done, let's say alpha or something. You have an extra condition that all variables that you have must be integers. Okay. Maybe you are working for some industry or factory where you want to find the optimal number of products that they should make on machine 1 or machine 2, those kind of problems that you did in your schools. So there you can't have values like you make 5 by 2 number of product 1. There you can have only integer values of product that can be made. So those kind of problems comes into integer programming problems. There are methods like, I'll just tell you the name, branch and bound. Okay. These are methods that are used to solve these kind of problems. Okay. Second thing is called mixed integer programming. Okay, let's come to mixed integer programming. So in mixed integer programming, some variables you want them to be integer. Okay. And for others, you need, for some, you don't care. Okay. Some you can allow them to be complete real numbers, but some you want to be, some you want them to be integers. You don't care. Okay. So that kind of problem is called mixed integer programming, MIP. Okay. I think IIT Bombay is also having a workshop on mixed integer programming this time. It's a very famous workshop called MIP. And earlier, this is the first time it is happening in India, and it's in our department only, mixed integer programming. If some of you are interested in these kind of things, you can probably apply. I don't think it's free, but yeah, if your institute supports you or your company wherever you are working supports you, you can definitely join. Yeah, so this is mixed integer program. Okay. Okay. So this is what I had prepared for today. This is the content that was covered in this week's lecture. If you have any doubt, you can please ask. Okay. And then we can